Did you recover from that last video? I added some more to that page. We're going to call this mess up here an algebraic representation. Rather than array, we'll call this the algebraic representation of array, and rather than calling it a vector that represents the array, we're going to call it a spinor. Vector, spinor. Vector, spinor. And in 2D, which is what we're working in, two-dimensional, that ends up being a spin 1/2. And that 1/2, or the 2 in the denominator, kind of tells us whether we're going to have to use, guess what? Half angle formulas. Okay, we just talked about a spinor. So isn't this interesting coincidence? I have spin up atoms and spin down atoms. I wonder if there's a relationship between those. Well, let's look at this setup here. We've got this strangely shaped magnet. So we got this one comes to a point, and this one's got a little dish out of it. And somehow we're sending atoms through this, and they're deflected. Well, you say, oh, yeah, okay, that's no big surprise. That's because they're charged particles, and the magnetic field moves the charged particles. But wait a minute, these silver atoms are neutral. They're not ions. So what is this oven thing all about? Well, the oven heats up the sample of silver, and it produces kind of a silver gas where you have individual silver atoms, and then of course they all come out at all different angles. These two, they're called beam collimators, but actually they're just a little slit there so that we can focus all of the atoms that are going in this direction. The atoms that are going off in the side directions, we just ignore those and get rid of them. But the atoms that are moving in this direction line up with that little point there on the magnet. And what we expect to see is that if there's some deflection, that deflection would be uniform up and down. Well, guess what? We only got two outcomes. Two outcomes, and that's it. And this kind of suggests that it's a two-dimensional structure. And that two-dimensional structure is what we've called this spin up and spin down, and we'll see that it follows the spinor that we just described. What would happen if we just selected these atoms? These are the spin up atoms. And then we pass those through another magnetic system. So we've got two sets of magnets. One that selects out the spin up atoms, and then we rotate that fixture around so that we get more than just one result. Well, it turns out we can get a probability, and that probability that we measured is proportional to, guess what? Theta over 2. So you've actually got to rotate the apparatus around not once, but twice to get back to where you started with just the spin up atoms. So this thing kind of verifies what we've been talking about. That last piece of information went by pretty darn quickly. So I've put this drawing up here to try to help us think through stuff. Let me get this pointer set up so I can guide us through it. I'm just going to call, rather than the silver atom, I'm going to call this the electron of the silver atom that matters. And you say, what? I don't get that. Well, let's see this. The electron moving towards you, that's the unpaired silver electron. it's going to take some discussion here, because what difference does it make whether it's paired or it's unpaired? Well, you just have to wait. Keep watching these videos, and when we get into hydrogen atom and other quantum chemistry, that'll be pointed out. But for right now, this is the reason why silver was chosen, because it had this one unpaired silver electron. So let's just, again, back to this electron. I'm talking over myself, but let's just get this electron. This electron is moving this way into the magnet. And from that last diagram, or that last picture that we looked at. Now let's look at it head on. So we are the detector. So we become the detector. We've got this electron's going to go right at our eye. So here it's coming down the line, and it's right underneath this little pointy part of the north pole of this magnet, and here's the south pole of that magnet. I'm not going to draw magnetic force lines, because that's just a picture. We got to get away from pictures. But this is something physical. There's actually is an electron. There actually are two poles of a magnet. So this thing is coming toward us. And if this spin property is two-dimensional, then that spin property can be in any of these directions. Wouldn't you agree? It could be towards the North Pole, could be towards the South Pole, could be over here, could be over there. That spin property, if it's directional, which actually is the magnetic moment that is created by that spin property, then you'd think it would, some of them would go towards the North Pole, some would go towards the South Pole, some of them would go this way. So think of these magnets as just our measurement device. And the amount of deflection gives us the answer or the measurement. So let's look at this closely. This is very important here. What we get is, if it's aligned, so let's just call it aligned. Who knows what that means? We'll call this, the spin is aligned if it's deflected towards the North Pole. And if it goes the other way, towards the South Pole, then it's completely non-aligned. Well, wouldn't you think the spin could be kind of in between aligned would show up? But that's not the case. We only get two different outcomes when we measure it. Now that doesn't mean that the spin only had two results, because as we saw, the spinor has all kinds of rays involved there. So something happens here that we've got to get our head around. Somehow there's some property that keeps this thing from going more than one of two ways. And there's really only one measurement we're making. We're only measuring one spin, and it's either aligned or non-aligned from our outcome. Now what happens to, it's easy to think of, if the spin on the electron is exactly aligned with the North Pole, then it's going to go towards the North Pole. Good, that makes sense. But what if the spin and do the other one, if it's completely non-aligned, then it's going to go the other direction towards the South Pole. But what if it's aligned somewhere in between? Well, what happens is that's called a superposition. And that superposition just gives us a probability of where it's going to go. And just to make things simple, because I think we're ready to tackle this idea, if it's right in the middle, if the spin is exactly in between the north alignment and the south alignment, then it's going to be a 50-50% probability of it going up or down. But it's going to do one of the two. It's not going to stay in the middle. That's why we've only got two outcomes from that experiment that was shown.